So it's a great pleasure and honor to speak at this celebration of Albrecht's scientific life. I confess I haven't looked up what was Albrecht's first paper 70 years ago. I'm sure it was a groundbreaking contribution, but I'm more familiar with another groundbreaking contribution of his 50 years ago. This was his joint work with Belyavin, Polyakov, and Tyupkin, where they constructed explicit solutions, incertain solutions of Yang-Mills theories. And I think it's fair to say that it has revolutionized our understanding of gauge theories and ultimately paved the way for the mid-90s breakthroughs in understanding non-perturbative dynamics of supersymmetric gauge theories and string theories, which is my background. So I first met Albrecht, I think, at the workshop here in June 1999. And this has led to a joint paper together on Morita equivalence and T-duality, which I'm afraid is mostly forgotten, but that's life. But it's, on the other hand, Albert's work was quite influential on me and many other researchers working at this juncture between high-energy theoretical physics and mathematics. And in some ways, he epitomizes the idea of physical mathematics, which is quite different from mathematical physics. And so I'm very honored to be able to speak on this occasion. So today I will discuss some mathematical relations between various enumerative invariants of a Calabi-Yau threefold, which were by and large discovered by thinking about non-perturbative aspects of string theory compactified on this threefold. So this includes, in particular, understanding the spectrum of BPS states, which are largely non-perturbative objects, as well as instanton corrections to the low energy effective action, which in fact, as I argue, turn out to be closely connected. One of the main physical motivations for these studies is really to try and understand the microscopic origin of the Bekenstein-Hawking entropy of black holes. And for that, so you know, I suppose, that these black holes are having a certain horizon area, carry a thermodynamic entropy proportional to that area, and there's been a long-standing question to understand this entropy in terms of microscopic degrees of freedom a la Maxwell. But for this, you need to quantize gravity, and so that's what the string theory offers, and it translates this counting of macrostates in terms of certain counting of so-called de-Bruijn wrapping cycles in internal space. Ultimately, it becomes a mathematical question which, about computing certain enumerative invariants and understanding their behavior at large degree. In general, so there is a clear physical prediction, but understanding it mathematically is very hard. And in fact, one of the few tools that we have for this is when certain generating series of these invariants satisfy modular properties, which give us very good control on their growth. So that's why my title is about modularity of Donaldson-Thomas invariants. But first I'll review some background material and some other relations with invariants that may be more familiar to you. And I should say this is loosely connected to Albert's work about almost 20 years ago now with Maxim and Vadim Vologodsky on certain integrability property of coefficients of periods in Calabi-Yau threefolds, and later on with Johan Elsbacher. So I hope Albert can relate to some of the topics I will discuss now. Okay, so the first type of topological invariant or enumerative invariant that I'm interested in are Gromov-Witten invariants. Of course, at IHES, I hardly need to define them, but just to set the notation. So these invariants count genus G curves, so n beta G. Beta is a class in second homology, counting genus G curves, sigma in the target space, which is a smooth, assume it's a smooth projective Calabi-Yau threefold. More precisely, there are integrals over the moduli space of Stemel maps of mgn into X.
You mean sigma into X?
Yeah, sorry, yeah, absolutely. Sigma into X. So there are integrals over that moduli space of maps. And so they are robust under complex structure deformation. They depend only on symplectic structure. But they are not actual integers in general. They take rational values. And the way they arise physically is when thinking about corrections to the low energy effective action in 4 dimensions, after one has compactified string theory on this Calabi-Yau threefold. 4 dimensions, there is of course the Einstein, Hilbert, and Maxwell terms, but then there are some higher derivative corrections of the form Riemann square times some power of a so-called graviphoton field strength, which is like a photon field strength. And the coefficient of these interactions are functions of the Kähler moduli, if we are discussing type 2a, and they are in fact entirely determined by these Gromov-Witten invariants and beta g. So you construct a generating series of those with a chemical potential T coupled to this homology classes. So this was pointed out already back in 93. And well, how do you compute those numbers? Well, of course, it's a hard enumerative problem going back to the 19th century. But the discovery of mirror symmetry has given very efficient or powerful ways of computing them, at least at genus 0 and genus 1.
Excuse me, I have a question. In this exponential, it's purely absolute value 1, purely imaginary exponential, or the convergent will it be?
No, so this T is the complexified Kähler parameter, so it is convergent. Yeah, T would be in some upper half plane. Yes. All right. Yeah, so mirror symmetry gives us a powerful way of computing them at genus 0, also genus 1. To go beyond this, in fact, it's been very useful to use certain holomorphic anomaly equations which control a certain non-holomorphic extension of this generating series. So this was developed by BCOV around the same time as this paper. And essentially, it allows us to bootstrap the higher genus invariants from low genus up to some ambiguity, holomorphic ambiguity, which needs to be fixed at every step. And the way this ambiguity is fixed is by requiring certain behavior at the boundaries of Kähler moduli space, or on the mirror side boundary of complex structure moduli space, namely on the discriminant locus or certain points of maximal unipotent monodromy. And well, this only gives a finite amount of information, but which is sufficient to go to pretty high genus. In fact, for the quintic threefold, which is kind of the iconic example, or in some way simplest example of Calabi-Yau threefold, it was, you can count the number of ambiguities and convince yourself it could go potentially up to genus 51, and then you ran out of data. Actually, this prediction was made in 2006 by Klemm and collaborators, and has just been achieved computationally very recently. And in fact, some of the work that I'm going to talk about allows to push this to a higher genus.
What do you mean by anomaly? What do you mean by the anomaly?
Yeah, so these functions here are clearly holomorphic, but the actual functions which enter the low energy effective action are some functions of T and T bar, which reduce to this as you take T bar to I infinity. And it is for those functions that there is this hierarchy of equations that relate them. So eventually the generating series are holomorphic, but behind the scene there is a non-holomorphic object which is globally defined on Kähler moduli space, and for which these conditions apply. Can't really say more, but I'm happy to talk about later. Okay, so however, these are not exactly counting objects. They give us rational numbers. And it turns out that there is some hidden integrality which becomes apparent if you reshuffle this, so these Gromov-Witten invariants entering in this partition function here into a new set of invariants, also labeled GV, beta, and G, also labeled by a curve class and a genus, obtained by equating, so expanding both sides of this apparently ad hoc equality in powers of lambda and e to the t, and equating coefficients. So this is some kind of multi-cover formula which for genus 0, it becomes much simpler. So basically the GV invariants at genus 0 for curve beta are equal to the Gromov-Witten invariants if beta is primitive. Otherwise, they are sum of all divisors of beta, 1 over k cube n of beta divided by k. And I think part of Albert's work was to understand the integrability properties or to prove integrability properties of these objects at genus 0. But really, this defines a whole tower of them for arbitrary genus. In fact, it has by now been, so if you take this as a definition, it has been proven by Yonel and Parker that those are indeed, using method of symplectic geometry, that those are indeed integers. And moreover, that they vanish at fixed degree beta if you go to large G.
So is it known for which genus, maximal genus, is approximate to a given beta?
Yes, so in fact, as an outcome of our work, we get the precise bound for this genus, so-called Castelnuovo bound. I think it's the first proof. I mean, it was conjectured in the literature, but I think now we have a rigorous proof, as I'll explain later. Now, this equality looks pretty dark. Physically, it comes from the following picture. So this GV invariance, Gopakumar-Vafa, counts certain bound states of so-called D2 branes wrapping a curve a curve of homology class beta, as well as, in principle, an arbitrary number of D0 branes. Turns out this number of bound states is independent of that. So that's for the genus 0 Gopakumar-Vafa invariant. Whereas the higher genus guys actually keep track of the angular momentum of these particles. I will be a little bit more explicit on the next slide. But once you have this picture in mind, then this formula really comes from a one-loop computation of the effective action in this constant graviphoton background by integrating over, summing over all particles, all these BPS particles that run into the loop, coupling to this background, and that's how you end up with this strange-looking formula.
So this power 2g minus 2 is coming from the power of W, which was previously 2g.
Well, it's related to the spin of the particles that run in the loop. And sorry, the question was?
I mean the graviphoton background.
So the graviphoton background, yeah, is proportional to this topological, so lambda, which, as you can see, plays the role of the string coupling. Okay. Now, let me explain this a little bit more. So, in fact, the better picture than these D2 branes wrapping cycles is to remember that type 2 strings come from M theory, so compactified on a circle. And when in M theory, you have something which are called M2 branes, the objects which have two space-like dimensions and one time direction. And they can be compactified on the curved inside X. And those are now black holes living in 5 dimensions, right? We start from 11 and we compactify in Calabi-Yau, we end up in 5 dimensions. So in general, they would carry an angular momentum given by some representation of the rotation group, which is SO4. So 2 angular momenta, J left and J right. And the precise statement is that if you keep track only of J left, or in particular its projection along the z-axis, then the translation between this GV invariance and the actual number of states of given charge beta, angular momentum m, is given by this combination of GVs weighted by binomials, where the sum here is finite because of this Castelnuovo bound, which I mentioned previously. And so here you can try to test this idea that the number of states should grow like exponential of the area of the black hole. There is a prediction. So you can compute the area of these 5-dimensional black holes. It goes like square root of beta cube minus m squared. And so that predicts this such a growth. There's no analytic control, as far as I'm aware, on which would allow to establish it. But there is numerical evidence which shows that indeed this works very well. Now, so mathematically, this GV invariance can also be defined independently as from this brain picture as actually counting some stable sheaves corresponding supported on curves with corresponding chain character. So this is a very complicated story, which I cannot really understand being a physicist. But Maulik and Toda have developed algebraic geometric methods using previous sheaf to define them. And those are then manifestly integer, but it's an open problem to explain why they are related to Gopakumar-Vafa invariants by the previous formula. So there are many open problems in this story, just thinking about counting curves. But what I want to do is to count some higher dimensional objects, namely surfaces. Yes.
Is it understood how the Maulik-Toda definition relates to the M theory picture? I mean, will it come from there? Or?
Well, it's motivated. I mean, at some low level, it's motivated by it. I mean, they have very good mathematical reasons to do what they do, and actually, it should be put in the larger framework of Donaldson-Thomas invariants, which I'm going to explain in a few minutes. Okay, so I want to add some other charges, namely the charge corresponding to a 4 cycle, and maybe the charge corresponding to the 6 cycle, which is the Calabi-Yau itself. So it turns out that it's easier to add some 6-brane or 6-cycle charge. So instead of considering this 11-dimensional theory M compactified on the Calabi-Yau times the circle to get down to string theory, one could actually replace the circle times R4 by another curved space-time called Taubnut space. It's a gravitational instanton. So it's another instanton in my story, I guess, which looks like a circle times R3 at infinity. So it has the same behavior at infinity. It's just that there is some kind of cigar and which is smooth in the interior. And in fact, as one reduces M theory on such a geometry, arguably one obtains a so-called D6 brane in type 2 strings. So D6 brane is just changing the topology of the 11-dimensional space-time, but it still preserves, it's still a smooth, locally flat space. And so the expectation would be that the same, what I wrote here, the same low relation, the same computation of the low energy effective action holds. And so the partition function of those objects would be the same topological string amplitude as before. Now, the good thing about these objects is that they, again, have a very precise mathematical definition, this counting. So I'm talking about these bound states of D6, one D6 brane. It's important that there is only one, otherwise there would be some orbifold singularity. And then some arbitrary number of D2 and D0. Well, this is mathematically described, as shown by Pandey and Thomas, by the theory of stable pairs. So stable pairs are the data of F, which is a pure one-dimensional sheaf, which encodes the curve class, as well as a section S from the structure sheaf to F, which has a 0-dimensional kernel. So the kernel corresponds to the position of these D0 branes. Now, it turns out that the moduli space of such stable pairs is a very nice object. And so you can extract the topological invariant from it, namely the Euler characteristic weighted by a certain Barron's function. And in this way, you obtain manifestly an integer. So the statement is then that the partition function of these PT invariants by this logic should be equal to the topological string partition function, which is this sum of this sum of Gopakumar-Vafa invariants of higher genus. So this is a rough prediction, but it was turned into a mathematical identity by MNOP. So that's Maulik, Nekrasov, Okunkov, Pandey. But essentially, it's using the previous relation to GV invariants. You can, if you take the exponential on both sides, well, actually the exponential is already taken here. You massage a bit the exponential. You can rewrite it as an infinite product. So this is the same GV invariants which appeared in this translation from GV from Gopakumar-Vafa to GV. And so now we have a very precise relation between the PT invariants and the Gopakumar-Vafa invariants. Now, the way you should read this relation is that a formal series in Q, which is conjugate to, well, in Q and e to the 2 pi I t. So you can expand on both sides order by order. And so it's fairly easy. So remember that there is some maximal genus. Okay, this capital N should be GV. I'm sorry for the mismatch of notation here. So because these GV invariants are 0 up when the genus is too large, you can pick up the leading term in this expression and see that if you are close enough to this Castelnuovo bound, which means if N is as negative as it could be, 1 minus G max of beta, then these PT invariants are again linear combinations of GV with some binomial coefficient, which however is a little bit different from the one I explained I showed on the previous slide here. Well, it's a technicality, but you have 2G plus 2. On the other side, you have 2G minus 2. The two quantities are closely connected, but not exactly the same. But nonetheless, they should, so this, however, is only true close to Castelnuovo bound. Otherwise, you see that if you expand to higher powers in Q, you will bring down some nonlinear terms in these GV invariants, and so you get this plus additional polynomials in GV. But so this relation was proven, I think, for toric Calabi-Yau at the time, and I think now is proven in, I believe, in full generality, although this maybe requires qualification. And so this gives some universal relation between these PT invariants coming from counting sheaves and these Gopakumar-Vafa invariants coming from Kolmogorov-Witten theory. Well, it would be useful to introduce actually a variant of PT, which are the so-called DT invariants. They differ slightly in the way one treats these D0 branes charge, which is the point class, associated to the point class. Essentially, the two generating series are related by a power of this Mach-Mahon function, which counts planar partitions. But both of them essentially count bound states of D6 D6 branes wrapped on the full Calabi-Yau along with some curve class and point classes. Now, so the real target of my talk is to count D4 branes, because that's where we expect modularity. But I need to take this detour because we're going to relate this D4 brane counting to exactly the objects that I've introduced. Now, the way we relate them is actually by using so-called row crossing arguments. And so the setup for this, and generally for the question of counting BPS states in Calabi-Yau compactifications, is the category, the bounded derived category of covariant sheaves on this Calabi-Yau threefold. So that is the mathematical realization of the category of BPS states in this setup. So the objects in this category are bounded complexes of sheaves with arbitrary homological degree. Physicists think of the morphisms between sheaves as open strings stretched between D6 branes and anti-D6 branes. I think the audience here is mostly physicists, mathematicians, so I can probably spare the physicists' jargon. What's important is that inside this derived category of covariant sheaves, or triangular category more generally, one can define a notion of stability condition. And eventually we're interested in counting stable objects. So the stability condition was introduced by Bridgeland, the notion of it. So it's generally a pair, ZA, where Z, the so-called central charge, is a homomorphism from the charge lattice, or the K theory of the lattice, to the complex numbers. It measures the mass of these BPS states, And A is the so-called heart. So it's an abelian subcategory of this big derived category. Satisfies many axioms. I guess the simplest of them being that the imaginary part of the central charge should be bigger than 0 for any object in the heart. If it vanishes, then the real part had better be negative. So those are questions which are, well, axioms which are easy to summarize for a physicist, but it turns out that the whole notion is extremely constrained and in fact very, very hard to construct. So if there exist stability conditions, Bridgeland has shown that the space of such things is actually a complex manifold whose dimension is the dimension of the lattice. In other words, you can specify the central charge for any basis vector and then use linearity. At least you can, if you know one such stability condition, you can perturb independently these central charges. But you have to make sure that it's non-empty. And in fact, it's only for very few examples that there is a mathematical construction of such a stability condition. I think this probably the state of the art is still that within the class of projective Calabi-Yau threefolds, it's only for the quintic threefold and a couple of other examples, degree 8, degree 10. But it's an open problem in general to construct such boundary conditions. And even in those cases, they are really only constructed in the vicinity of the large volume point. Turns out there is a strategy to do it for arbitrary threefolds, which relies on some inequality, which actually will be very important, and I'll come to it somewhat later. But let's leave it at that for the moment. Now, once we have this stability condition, we can ask what are the semi-stable objects. So consider this moduli stack of semi-stable objects. They are such that for any sub-object E prime, the argument of the central charge should be less than the argument of E. This is so this is a very complicated moduli space, a moduli stack. Nonetheless, there is a way to attach to it a rational number called the generalized Donaldson-Thomas invariant. And of course, Maxime and Jan Zommelmann have made very important contributions to this topic. But it is still, by construction, a rational number. And then the conjecture is that if you apply some multi-cover formula of this type, so with 1 over k squared now, then the resulting number should actually be an integer. And I think that's a theorem in the context of category of quiver representations, but in this level of generality, it's still a conjecture. Now, importantly, this number being is integer, but it may jump on certain walls, so that happens whenever the central charge, well, this condition gets saturated, so when the central charge Z gamma prime or Z E prime aligns with Z of E for some sub-object. And so there is a famous and universal formula that determines the invariance on one side of the wall from the invariance on the other side of the wall. And that will be a crucial ingredient for my story. And in part, so we have, so in particular, if we have this space of stability conditions, which allows to extrapolate to infinite volume, then one can show that this dt invariant omega of gamma, I should have said maybe that gamma was the Chern vector, so I write 4 entries here. This is Chern 0, Chern 1, Chern 2, Chern 3. So this is the rank. So this is D6, D4, D2, D0, or if you like, Calabi-Yau, divisor class, curve class, and point class. So in this limit, this dt invariant will coincide for those charges. If there is only curve class and point class, they will coincide with GV at genus 0. Whereas if there is one unit of D6, it will coincide with this PT or maybe this GV invariant at large volume, depending exactly how you approach the large volume limit. Okay. Now, coming finally to the main interest of my talk, those are the so-called rank 0 dt invariants. So now I consider a a divisor P, a curve class beta, and some number, integer number n of points. And I want to count how many stable objects in this derived category have this chain character. In physics language, I want to count these D4, D2, D0 brane-bound states. Now, from the physics point of view, there is a very clear prediction for what those numbers, how these numbers should behave. First of all, about their growth, and second, about the properties of their generating series. So once again, if we think of this type 2 string theories as coming from 11 dimensions on the circle, well, in 11 dimensions, we have these so-called M5 branes, which have 5 special directions. And if you reduce 5 of these dimensions on the divisor inside the Calabi-Yau and the 5th one on the circle, well, in fact, you get exactly these 4 branes wrapped on the divisor. But the advantage of this is that you could stop halfway, just reduce on the divisor, and you'll be left with some string after reducing on 4 directions. And so that string supports some two-dimensional superconformal field theory, which is supersymmetric. And in particular, it has, so it looks a bit like a sigma model into some moduli space of the divisor and the sheaf on it. But it has an invariant, a quantity which is robust on the deformation, and that's the elliptic genus. And so the physical expectation is that these numbers here are actually Fourier coefficients of the elliptic genus. Elliptic genus is the partition function of this SCFT on the torus, so it's a function of tau in particular, the modular parameter of the torus, and so it's expected to have modular properties. I'll be more specific in a second. But at least you can, from these properties, you can, and very small information about this theory, namely just the central charge, you can predict the growth of these coefficients from the physics point of view. And, well, the growth is determined by this Cardi formula. Yeah, so it goes like a square root of the central charge times n. N is essentially the momentum along this circle. And so you predict, well, it matches exactly the prediction, again, from Bekenstein-Hawking formula, which is this time square root of p cubed times n. P cube is the self-intersection of this, the cubic self-intersection of this divisor.
How does this factor 1 over half here? The
factor here? Well, I mean, you could, for this argument, I'm ignoring both of them, actually, but there is some index theorem which allows to compute the central charge from the data of the divisor. This was developed in this Maldacena, Strominger-Witt, and Starry. But one of them comes, as you see, from the Euler number of, I think this is the holomorphic Euler characteristic. Yeah, actually, I don't remember exactly the details, but those formulas are easy to obtain. But so that determines the growth of these coefficients, but doesn't tell you what they are in the first place. You still need to, you would need to solve this two-dimensional theory. But of course, modularity is a very strong constraint. So maybe if you can compute the first few coefficients in this elliptic genus, then you can actually bootstrap and obtain the full generating series. That's the strategy. Now we have to be careful here because of these wall-crossing issues. So if this divisor is primitive, one can show that there are no walls which extend to large volume. And so it doesn't matter which chamber I choose to evaluate this DT invariant. And then the physics prediction is that the elliptic genus, which is given by this, so this generating series here, so it's basically a sum of all possible values of the point class n, q to the n, with some decoration here, which improves the modular behavior. But the physics prediction is that this should be a vector-valued, weakly holomorphic modular form of a fixed weight. In fact, it transforms in a veil representation of the lattice H4 of X with the quadratic form induced by intersection with this divisor P. So why is it vector-valued? Is because so I'm fixing this divisor class P, and I'm also fixing so mu is in fact also the curve class. It turns out that, yeah, I write this on the next point perhaps. I did not, but it turns out that the dependence on mu is periodic. Essentially, by tensoring with the line bundle, we can get rid of this curve class, except for this discrete information. So this is a finite group. And the other point to note is that the sum is actually bounded from below, so it converges by this Bogomolov-Giesecker equality. Okay, so that's the physics prediction, but only when the divisor is primitive. In general, it may not be, and we predict. So we have been basically investigating this problem with Sergey Alexandrov and Jan Manschott for several years with different motivations, and we came out with a very precise prediction for the modular properties of this object in the general case, namely. So first of all, you need to specify at which point you should evaluate this, because now there is recrossing phenomena. The specific prescription is this so-called large volume attractor point. So it's a different point for every class. I don't want to elaborate too much on this. But the main point is that, so if P is non-primitive, then it should not be modular, but so-called mock modular of depth k minus 1, where k is the largest divisor of P. So what does it mean to be mock modular of higher depth? Well, it means something very precise. It means that there is, so if you construct, so you're interested in properties of this joining series HP, and I'm suppressing here this other index. Well, it's not going to be modular, but there is a very precise prescription to construct a strictly modular form out of it by combining it with the joining series for the possible components, irreducible components of P, and that new series is modular, but it's not non-holomorphic anymore. So this theta series here is a non-holomorphic Siegel type theta series, which is entirely predicted by physics. And so the new object is modular, but it satisfies a non-holomorphic anomaly equation. If you hit it with d by d tau bar, it essentially acts on this theta series and produces, it relates it to the modular completion of the constituents themselves. So it's a long story, and took us many years of work to arrive at a very precise prediction for this completion. And in fact, the strategy was to think about instanton corrections, but instanton corrections in 3 dimensions after wrapping our theory. Remember, we are counting BPS states in 4 dimensions after compactifying on the Calabi-Yau. But if we reduce further on the circle, we get down to 3 dimensions. And the nice thing is that all the black holes or BPS states that existed in 4 dimensions can actually wind around this time-like circle and give instanton corrections in 3. Yeah, and that's so it's in 3 dimensions. Where there is a complicated moduli space metric, but exploiting all the constraints from supersymmetry, and most importantly, from the action of this manifest SL2Z symmetry, which is apparent because after reducing on a circle, we now have like M theory on a 2 torus. This has a manifest SL2Z action. Then it led us to this very non-trivial prediction for this series.
What is the depth?
So a modular form of depth 1 would be such that if I hit it by a tau bar derivative, it will be the complex conjugate of an ordinary modular form. And so you just recursively apply this definition to higher depth, right? You could give a more formal definition, but that's the idea. Okay. So I see that time is running faster than expected, as usual. Now, for the mathematical point of view, this modularity property is very surprising. In fact, I think the only case where we know where it comes from is when we can relate this invariance to a notor-Lefschetz invariance. So maybe I should not spend too much time on this, but if the Calabi-Yau happen to be K3 fiber, then if you look at this these branes wrapping only the K3 fibration, and you can relate these numbers, these Donaldson-Thomas invariants, to the notor-Lefschetz invariance of the fibration, which are some kind of intersection number with an arithmetic cycle in the moduli space of K3 manifolds. And then by results of Kudla-Milson and Borcherds, you actually prove that they are modular. Another place where it's known, though not very well understood, is if you take a non-compact Calabi-Yau threefold, for example, the canonical bundle over some surface, some Fano surface, then these DT invariants reduce to Vafa-Witten invariants. There are invariants for the moduli space of sheaves on this on the surface, and well, in some simple cases, one can compute them explicitly and check modularity. Although I think eventually it should come from some kind of VOA acting on moduli space of sheaves, but that's still an open problem. Okay, so the aim in the remaining, I guess, 20 minutes or so is to actually test these predictions in the context of the simplest possible Calabi-Yau threefolds, namely those which have pK rank 1, so just a single Kähler modulus, such as the quintic. And the strategy would be to compute the first few coefficients in this Q expansion and then try to match them to some putative modular form or mock modular form. This was actually attempted already almost 20 years ago now by Gayotto, Strominger, Yin for the quintic, as well as a few other hypergeometric models. So there is a rather, well, okay, I don't have the list here, but there is a list of 13 such models where you can apply this strategy. But they were essentially doing guesswork, and they were very lucky. Now we want to give an actual rigorous computations and the test to compute as many numbers as possible to test modularity in as much detail as we can. Okay, so now this is coming to the meat of the talk, which is how do we compute this rank 0 DT invariance? Well, turns out that Richard Thomas and Soheyla Feyzbakhsh over the last few years have developed very increasingly precise relations between rank R DT invariance and rank 1. So the rank, recall, is the D6 brane charge. So rank R would be R units of D6 brane charge. We're interested in R equal to 0. And so these two fellows have established universal relations between any R, in particular R goes to R equals 1, where we can relate them to GV invariance. So let me outline the key idea of their approach. So the idea is to use wall crossing, not in the full space of brilliant stability condition, because we don't know much about it, but in fact, in a slice of weak stability conditions. So we can relax some of the axioms, still maintaining consistency with this wall crossing formula. And in fact, this slice is motivated physically. There are various reasons for choosing this particular slice. The main reason for mathematicians is that this is actually the first step in constructing Bridgeland stability conditions in a genuine sense. So it goes in a kind of two-step procedure. First start with the abelian category of current sheaves, then perform a tilt with respect to the slope, and then on that new heart, construct this particular central charge, and then perform a further tilt. Now, so this central charge here, as you see, is a linear combination of the Chen characters of Chen 0, Chen 1, Chen 2, Chen 3. And it's unphysical in the sense that it doesn't depend on Chen 3. But again, you can use it as a stepping stone to then go to the physical one, or to the large volume one eventually. So the CHBK here is the integral of CHE times e to the minus BH. H is the polarization of the Calabi-Yau threefold. Okay. And then for this particular, so for this weak stability condition, the heart is very simple. It's just obtained by twisting tilting according to the slope CH1 minus B CH0. So this I already said. So this wall crossing formula works in this family, and it includes at large volume. So large T is large volume. It includes this Giesecker stability or large volume stability, where we are interested to evaluate these invariants. But compared to the genuine stability condition, the structure of the walls are actually extremely simple. So if we plot them in this half plane, B, so B is the B field, and W is 1/2 B squared plus 160 squared. The 1/6 is not very important. So the actual space of stability condition is above this parabola. Then it turns out that the walls are just straight lines in this plane going through 2 points which are easily determined in terms of the Chern classes. And more importantly, there is, depending on the Chern classes, there may exist a first wall, or given in red here, where there are no stable objects below that wall. So, in fact, so this property is instrumental for boosting this to a full Brillouin stability condition, and it goes under the name of the BMT inequality, Bayer-Macri-Toda. And it looks a little bit ad hoc, but it states that there will be no tilt stable object if, unless this inequality is valid. So you see this is a line in a WB plane given by this red line here, and the coefficients depend on the Chern classes. So if you have an empty chamber, then you can hopefully control all the walls to infinity and express the invariants of interest in terms of those occurring further inside. And if you're lucky, you can set up a kind of inductive procedure to compute these invariants. So in the original papers of Feyzbakhsh and Thomas, they just gave general existence proof of these relations. But in fact, one can give very explicit formulas. And so Soheyla Feyzbakhsh was actually our collaborator on this project, and she essentially gave the background, the mathematical work for this to happen. So in particular, one can, if we want to compute these PT invariants, for example, it turns out that if the charge, so if beta and n are large enough, then there will be there will be an empty region here, and sorry, what am I doing? An empty region under here, and a single wall as you go to infinity, where the only jump would be governed, in fact, by this dt invariant for a d4 branch charge. So this gamma here is 0. H is the generator of H4 beta n. Okay, and so the other component is actually just what I denote by anti-d6 brane is just the structure shifted by 1. So of course it has unit dt invariant. So in this way we get that PT is proportional to omega of this rank 0 omega. But we're interested in evaluating this rank 0 omega, so we can just divide as long as this is non-zero, and we get this relation, which is valid provided this beta n is large enough. So we can always tensor with some line bundle to make it to satisfy this size condition. I mean, so instead of using beta n, we can use beta prime n prime obtained by tensoring with a line bundle. But the cost we pay is that if we want to compute this PT invariant, to read off the left-hand side, we need this guy with higher and higher degree and genus. And of course, we have only limited information about this. So it turns out this direct strategy is not really good enough. But there is a refined version of this, which Soheyla established for us in this in an appendix of our joint paper, in which essentially will apply even if there is not just a single wall, but could be an arbitrary number of walls. So I had the full mathematical statement here. Maybe I don't know to what extent it's of interest to the audience, but the idea is that, yeah, if you choose, so M is the disorbitant charge and beta is the Kerr class as before. So if under a certain condition, which is that this kind of function fx is less than alpha, then this PT invariant of beta m will actually be expressed recursively in terms of PT of beta prime m prime, with m prime strictly beta prime less than beta. So this is a recursive procedure. So again, the walls, there is a finite number of walls which are of the form PT times rank 0 invariant. So they basically correspond to a D6 brane emitting a bunch of D4 branes as you go to infinity. And so at infinity, we have this PT invariant, and in the middle, we have, at the origin, we have 0. So in this way, we get an equality between the two. And as a consequence of this theorem, in fact, comes this Castelnuovo bound that Maxime was asking about. So using these arguments, we can establish that PT of beta m on the left-hand side is 0 unless m is bounded from below by a quadratic polynomial in beta. This is actually, this was conjectured already by Katz, Klemm, Vafa many years ago, and in the simplest case of P2 would come just from ordinary Castelnuovo theory. But this is actually a sharp bound. Okay, so time to present some numbers before closing. So just to impress you a little bit, perhaps. So using this formula, we have computed a large number of coefficients for the quintic as well as a few other models, and we could match them to this basis of modular forms. So the modular forms are actually quite boring. So this is, I should have said, this is for 1 unit of D4 brane charge. So there's no mock modularity in this example at first. So I wrote this here, 1 unit D4 brane charge. So the modular forms are just derivatives of theta series times some powers of Eisenstein series. Very boring. But yeah, this is the list of models where we could do this. And this is, for example, what we get for the quintic. Actually, it's only those that I could fit on the slide. We have more than those coefficients. But the point is that the dimension of the space in which this putative vector volume modular form is supposed to live is 7. It's given by the so-called polar terms in this expression. It's the terms which have an overall negative power of Q. So if you just compute those terms, you predict uniquely all the other Fourier coefficients. But in fact, we could compute them independently and match them on the nose. So it's a very strong confirmation of this modularity in the simplest case. Here is the full combination that matches them. On this case, it turns out that it reproduced the physics guess from Gaiotto and friends. But actually, in another model, they made a slightly less educated guess, and they got the number wrong. So we actually can compute this rigorously, assuming, of course, this BMT inequality, which, in fact, for X10 has been proved mathematically. So this is a solid result. All right, I had a few slides about the rank 2 case, and where we do have these mock modular properties appearing, and in fact there is some relation to Horvitz class numbers, but I feel that this is already far too technical, so I will just, I mean, you can see them on my slides if you're interested. And just that we do have checks of this level 1 prediction. So let me try to wrap up now. So I've explained some relations between Gopakumar-Vafa and Gromov-Witten invariants and this PT invariance on the one hand side, as well as this ranked 0 DT invariance on the other side. So this is where the modularity predictions hold. This is so the starting point is here. So we use mirror symmetry and these holomorphic anomaly equations to compute this Gopakumar-Vafa invariance to high genus as possible. Then we feed them in this relation to PT and use word crossing to get this to compute a few coefficients here. Now, if we believe, or we could show that this had to be modular, then we could use this kind of modular bootstrap to determine the exact series. And then we can feed this back into the loop and obtain new information about this Gopakumar-Vafa invariance. So there is a very virtuous kind of cycle going on between these different notions of enumerative geometry. And using this virtuous circle, we can actually push up the possible, the maximal genus which is accessible by using this integration of the holomorphic anomaly equations. So it used to be 53 for the quintic, for example, but using this modularity property, we can push it to almost 70. You might find that this is a modest increase, and I would agree. But it's still, I think, a non-trivial outcome of this strategy, and maybe on the longer term, it could help us narrow down new boundary conditions for this topological string amplitude and the higher genus, so-called quantum geometry. I think I probably have a couple minutes, so I just want to show this slide, which is trying to understand better what is the meaning of this BMT inequality, which is at the heart of the construction of Bridgeland stability conditions, at least near a large volume. So we don't understand it physically very well. I mean, mathematically, it's kind of tuned such that it will work, but I don't think there's a very conceptual understanding of it. What we can see from the physics side is that there is a very simple interpretation of the condition for existence of an empty chamber. So if you remember, this condition was linear in the parameters and quadratic in the Chern classes. And maybe I should go back to it very quickly. Here, this condition here. Okay, so this was quadratic in Chern classes and linear in B and W. But if we ask that this line lies above the parabola, we should ask that there are two intersection points with the parabola, so we get actually a quadratic equation in B. This is very simple mathematics compared to the rest. And then, therefore, we get a quartic condition on these Chern classes. Where is it? It's coming. Yeah, it is. So that's the quartic condition that ensures the existence of an empty chamber. But if we express it in terms of the charges of the black hole, we give, of course, the same quartic polynomial. But now it's easier to identify. This actually says that there is no physical black hole in this region. So this would be the square of the entropy. And it says that if it existed, it would have an imaginary entropy. So that's kind of satisfying from the physics point of view, although it doesn't explain the full condition, only the consequence of it. So an open question, I think, is, well, can we understand this BMT inequality physically, mathematically, anyway, perhaps using B model side or A brains, depending how you call it. And it also suggests that there are some improved version of it. Clearly, this is far from optimal. We see that many of our predictions would work if there was a slightly stronger inequality. So I think it's an interesting problem for the future. And here's just the last slide. So I think we have overwhelming evidence that these indices exhibit modular properties, even mock modular. What is the mathematical reason for it? Is there some VOA acting on the cohomology of modular space of stable objects? Can we find other methods to determine this GV invariance at higher genus? We can use the same story to also compute higher rank DT invariance. That would be like 2 units of D6 or higher units of D6. Is there a version of MNOP in this setup? And then going back to the issue of instantons, which was, I didn't use too much, but was essential for arriving at those constraints. So far, we only took into account instantons from D branes wrapping the cycles in the Calabi-Yau. But in fact, in string theory, there's also some other more exotic object called Neveu-Schwarz fibrane. It's not the same as the, well, it is the same as the fibrane in 11 dimensions, but not wrapping the full Calabi-Yau. And so it's probably some very interesting mathematical structure underlying those things, and it remains to be uncovered. So this is it. Congratulations again, Albrecht, and I wish you many more scientific achievements in many years and the health that goes along with it. Thank you.
Thank you very much. Questions, please.
Can you comment on this? You said the VOA acting on the moduli of stable objects. What is the expectation coming from physics? Like, is there some physical picture that leads you to expect this?
Well, first of all, there is the case of locally Lie spaces and Nakajima's construction of this such a VOA on moduli space of instantons. So one would expect that this carries over, for example, to Vafa with an invariance. So this would be DT invariance on some local Calabi-Yau 3. This probably is realistic. The extension to the full non-compact guy is probably out of reach. But general idea is that nonetheless, if you have this fibrane theory that wraps this divisor, there is some 2D CFT after reduction, and there should be some kind of chiral sector which explains this invariance, and there should be some mathematical construction out for it.
So I have a question. One can, for this DT invariance, you have specified both charge and also a chamber, yeah? Mm-hmm. And there's a way to avoid specific chamber. You consider only DT invariance at attractor points.
Yes.
Yeah, and it will be encoded or
yes.
Can you analyze how it works for this absolute invariance in a sense?
Okay, so I did not emphasize it that much, but the way we define this journaling series was by using not quite the attractor chamber, but what we call the large volume attractor chamber is what you get by computing the attractor chamber and then taking a radial array to infinite volume. Eventually one would be interesting to compute the actual attractor indices. We know how to do this, by the way, for non-compact Calabi-Yaus, but in the quintic, the expectation is that most of these states would actually have decayed because there are some D6 bar that decay along the way. I mean, at this moment there is no physics prediction, partly due to the limitation of our analysis of these instanton corrections to moduli space, which was really near the large volume limit, where we can neglect these fibrane instantons. So yeah, honestly, so there is a sharp answer for non-compact Calabi-Yaus, but in the compact case, I cannot say anything.
Other questions? Let's thank the speaker again.
Thank you.